All right, so believe it or not, in this lesson, we are already wrapping up Unit 3. Okay, it's a short one, only 3 lessons. Okay, so we talked about exponential functions. Exponentials and those relationships obviously didn't really go away when we started talking about logarithms because logs and exponentials are very closely related, as we saw in the previous lesson. But today we'll finish up, we'll kind of start thinking about how logs let us solve exponential equations or work with exponential equations and open up doors that might have been closed to us before, okay? So as always, here's the little checklist you can use to check in with yourself after the lesson, after you've done your practice. Do you have those skills or do you need to work on them a little bit more or maybe reach out for some help? All of those are valid options, but take a little look at that afterwards and see how you feel. Okay, well, let's jump in. Okay, so we're going to start out by talking about something called the laws of logarithms, or the logarithm laws, or log laws, right? We talked about the exponent laws. I mean, we've talked about them in many previous math courses, but we did a quick reminder of them in the previous lesson, okay? Just a very quick recap. These are what we're talking about with our exponent laws, right? Again, they're not like magic tricks or anything. They're not things to be memorized. They make sense when we break them down. We do use them just offhand without having to prove them every time, but they are our product of powers. So if I have a to the m times a to the n, it's equivalent to a to the m plus n, adding those two exponents, which makes sense. You know, an example here to show it, x squared times x cubed, well, that's x times x times x times x times x, right? Which is a total of x to the power of 5. Add the exponents. Multiplying 2 factors of x by 3 factors of x gives you a total of 5 factors of x multiplied together. Okay. The quotient of powers, similar idea, except we're dividing two powers with the same base, right? A to the m over a to the n. We can just subtract those exponents. Again, makes sense. If we have x to the 5 over x cubed, that's saying 5 multiplications of x divided by 3 multiplications of x. Well, dividing by 3 multiplications of x, each one of those can just cancel out with one of our numerator multiplications of x, so that's why we're subtracting this off, right? For every exponent of x, or multiplication of x we had up here, we're losing one down here from that division, right? So we're dividing them off, leaving us with x to the power of 5 minus 3, or x squared, which is exactly what we can see happens here when we cancel out all those x over x, okay? Power of powers, that's what we get when we have a power being raised to some exponent. So a to the m, but then a to the m is all being raised to the power of n. That gives us a to the m times n. Again, makes sense. For example, x cubed squared, that's taking an x cubed, an x times x times x, and multiplying it by itself, another x times x times x. So in total, you've got x times x times x, times x times x times x, or x to the power of 6, right? 3 times 2, 6, okay? If this were a 3 instead of a 2, you would have x cubed times x cubed times x cubed. So that would be x times 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 x, which is x to the power of 9, right? 3 times 3. So that one makes sense. Power of a product, that just says if you've got two things multiplied together, ab to the power of m, you can equivalently write that as individually a to the m times b to the m. Again, makes sense. xy cubed is really just saying xy times xy, which is saying, if we rearrange that a bit and think about how we could simplify, well, the x times x part and the y times y part, that's just x cubed and y cubed. So xy cubed is equivalent to x cubed times y cubed. And then power of a quotient, very similar logic, but again, now we're dividing those two things. So a over b to the m is the same as individually a to the m over b to the m. Again, if we had x over y cubed, that's really just saying x over y times x over y times x over y. X times x in our numerators gives us x cubed. Y times y in our denominators gives us a denominator of y cubed. So sure enough, x over y cubed is the exact same thing as x cubed over y cubed. Okay, so we're just doing a quick reminder of the exponent laws before we do the logarithm laws, because these really are just the same ideas, but the log versions of them. So they're kind of based in the same thoughts and logic. And we will I'll go through the explanation, because I don't like to just give you, a magical law and say you have to follow it. Just trust me, it works, okay? But I will just give the disclaimer at the beginning that you don't have to come up with these on their own. So like this information, I am going to go through it because I think the explanations are helpful for understanding what we're doing and why it makes sense, okay? But they are all on your formula sheet. So ultimately, you just need to apply them. But applying something without understanding it is, not a great way to approach math. So we will break it down. But I just wanted to say that right at the top. You are given these on your formula sheet. I don't want you to think you have to come up with this on your own by going through this whole thought process here. Okay, you are given them. But let's go into the explanation of each of these logarithm laws. So again, just a reminder of that key relationship, because we're going to use it a lot in coming up with these log laws. We're just using it, right? The fact that log base b of a equals x, okay, this here, is the exact same thing as b to the x equals a, right? This to the power of this equals this. B to the power of x equals a. These are saying the same thing. So that relationship is going to come up. All right, so the first logarithm law, sometimes called the product of a logarithm law, okay? What it says is that if you have log base b of m times n, it's equivalent to splitting it up into two logs and adding them. So log base b of m plus log base b of n, okay? So that's what we need to actually use and apply, but let's not just take my word for it. Let's see why that actually makes a ton of sense when we break it down. Because remember, what log base b of m times n is equivalent to, it's just saying what exponent could we raise b to and get a result of m times n. To walk ourselves through this, let's just, pick a number that is the answer to that question, right? So there is some exponent that's the answer. Some exponent out there exists where b to the power of it equals m times n. We're keeping things general because we're trying to kind of prove that this rule makes sense. So we can't just pick numbers. We've got to keep it general so that it could work for any number. So there's some exponent that's the answer. Let's just say it's p. And therefore, log base b of m times n equals p, right? All I'm saying is that b to the power of p equals m times n. And log base b of m times n is equal to that power. Okay, whatever power b would need to become m times n. Now we're just going to apply that same logic here to the other parts of our law, log base b of m and log base b of n. Log base b of m is saying, similarly, what exponent could we raise b to and get a result of m, right? Log base b of m is the exponent that b would need to become m. So b to what power equals m, okay? And again, there's some exponent out there that is the answer. Let's call it q. And therefore, log base b of m equals q, right? B to the power of q, whatever q is, equals m, okay? Log base b of n, the last part here of our log law, is saying what exponent could we raise b to and get a result of n? There is some exponent that is the answer. Let's call it r. So therefore, log base b of n equals r. Again, just saying there, b to the power of r equals n. Right, so all we're doing is agreeing to define some of these logs as, what they're equal to, right? There is some exponent for this, some exponent that we could raise b to get m, some exponent to raise b to get n. We're just giving them names so we can think about how they're related to each other with some equations. So let's then just rewrite each piece of this law, meaning log base b of m times n, log base b of m, and log base b of n in its exponential form. Well, log base b of m times n equals p in its exponential form is just b to the power of p equals m times n, right? This one, b to the power of q equals m. B to the power of r equals n. Okay, now, since m times n is equal to, m times n, right? We could say that m times n is b to the p. So b to the p must equal m, which is b to the q, times n, which is b to the r. But our exponent laws, and really these log laws come from the exponent laws in many ways because logs and exponents are closely related, right? What does that tell us we could do here? We could rewrite this as b to the power of p equals, we're multiplying these two together, so b to the power of q plus r. So think about what that's saying. Whatever b is, when we raise it to the power of p, it's the same as raising it to the power of q plus r. So this can only be possible if p is the same thing as q plus r, right? How could I raise b to some number and then raise it to a different number and get the same answer? I couldn't, right? That's only possible, like if I did, 2 to the power of x equals 2 to the power of y, well, that can only be true if x and y are the same number, right? If they're two different numbers, these two things can't be equal. So same logic here. P must be equal to q plus r. P must be equal to q plus r. But this is where the kicker comes, right? Because if p is equal to q plus r, well, p is just log base b of m times n. Remember, right? P was just the power b would need to become m times n. And q was just log base b of m. And similarly, r was just log base b of n. So if p equals q plus r, then log base b of m times n has to equal log base b of m plus log base b of n. And there we go. We've just derived the first law of logarithms, the law of products, or the product law for logarithms. Okay? Now again, do you need to explain this for yourself in order to be able to use the law on a test? No, you're given the formula on your sheet. But now hopefully we kind of have an understanding of, oh yeah, that's not just some like weird symbols. I can kind of see where it comes from, right? Why this makes sense. Okay, so 1 down, 2 to go. So this next one here, you might be able to guess, this was called the product law of logarithms because we were multiplying. This one is called the quotient law of logarithms because we're dividing. And so it says log base b of m over n can be split up into log base b of m minus log base b of n. Notice very similar to this one, except, multiplication becomes addition of two separate logs. Division becomes subtraction of two separate logs. Do you see already, even just like on a base level, the connection between these and the exponent laws, right? When we multiplied two powers together, we ended up adding their exponents, right? When we divided two powers, we ended up subtracting their exponents. You can see the kind of inherent connection between these logs and the exponents, okay? But let's walk through the logic of this one. Log base b of m over n is saying what exponent could we raise b to and get a result of m over n? Again, there's some exponent out there, so for the sake of being able to write some equations and do some work, let's just say it's p. We'll call it p. So log base b of m over n equals p, meaning that b to the power of p equals m over n. Whatever p is, we're just saying that's the exponent that would make this true. Okay, and again, very similar logic here. I'll go a bit quicker because it's the same thing. Log base b of m is saying the same thing, except what could we raise b to and get a result of m? There's some exponent that's the answer. For the sake of being able to write some equations and think about relationships, we'll call it q. So log base b of m is just q, okay, whatever q is. b to the power of q equals m. Log base b of n, same thing. There's some exponent that tells us when we raise b to the power of it, we get a result of n, and we're just going to call it r. So therefore, log base b of n is equal to r, meaning that b to the power of r equals n. So let's now that we've kind of come up with some, dummy variables, essentially, placeholder variables, we can rewrite each piece of this law in its exponential form. So log base p of m over n we said was going to equal p. In its exponential form, b to the power of p equals m over n. Log base b of m equals q in exponential form, b to the power of q equals m. This one, b to the r equals n. Okay, now, since m over n is equal to, m over n, okay, we know that m over n is b to the power of p, but we know that m is b to the q, and n is b to the r. So we can say that b to the power of p is just equal to b to the power of q over b to the power of r. But our exponent laws, what do they tell us we can do with this? They tell us we can subtract, right? See where this is headed? So our exponent laws tell us that we could rewrite this as b to the power of p being equal to b to the power of q minus r, right? Just rewriting this using the exponent laws. And therefore, by the same logic, if b to the power of p is the same thing as b to the power of q minus r, well, that's only possible if p is the same thing as q minus r, right? How could I raise b to two different powers and get an equal thing? Well, I couldn't. They have to be the same thing. So p must be the same thing as q minus r. But once again, don't forget, we said p is log base b of m over n. That's where this all started. And q is just log base b of m, and r is just log base b of n. So if we now know that p is equal to q minus r, that must mean that since p is log base b of m over n, it's equal to q log base b of m minus r log base b of n. And there we go. We've now proven the quotient law of logarithms, right? Again, closely related to those exponent laws, right? And no, once again, you do not have to derive this yourself to use it on a test, but now we understand where it comes from. At least, hopefully we do. All right, 2 down, 1 more log law to go, and then we'll start actually using them. And so once again here, we kind of see the connection to the exponent laws, right? We knew that when we multiplied exponents or multiplied powers, we add the exponents, right? Multiplication, addition, connection. When we divide powers, we subtract exponents, that division, subtraction, connection. And when we had an exponent to an exponent, we end up multiplying. And you can kind of see an exponent and a multiplication. But let's prove why this last log law here makes sense. So what it says is that log base b of m to the power of n is equivalent to n times log base b of m. In other words, you can essentially take this exponent n and bring it down and make it a multiplier on the entire logarithm. Okay, now why does this work? Why does it make sense? Because log base b of m is, once again, it's saying what exponent could we raise b to and get a result of m, right? This is equivalent to the exponent b needs to become m, okay? Now, there is some exponent out there that is the answer, and for the sake of writing equations and thinking about relationships, we're going to give it a name. We're going to call it q. And therefore, log base b of m equals q. So let's just right away now, we're going to take a slightly different path here. We're going to rewrite this in its exponential form. So b to the power of q equals m. This to the power of this equals this, right? B to the power of q equals m. Same relationship, we've just written it in the exponential form instead of the logarithmic form. Now, since we're dealing with exponents and m to the n here, this might seem a little strange, but this often is a strategy in math, especially when you're proving stuff. You kind of try doing stuff to both sides and see if it gives you any idea. So let's raise both sides to the power of some number, n, to see if we notice anything. Okay, what I'm going to do is I'm going to raise both sides to the power of n. I'm allowed to do that. I'm doing it to both sides, so I'm not breaking any rules. Okay, and our exponent laws tell us that we can rewrite this as, since it's b to the q being raised to the power of n, I can multiply those two exponents together. So this has now become b to the power of qn equals m to the power of n. Okay, and now all I'm going to do is actually just rewrite this in its logarithmic form. So it seems kind of weird to, go to exponential and then back to logarithmic, but this is often how math proofs go, especially when we're first figuring this stuff out. We try some stuff and see if we notice any relationships. Okay, so I put it into exponential form, raised them to the power of n, and now I'm actually just going to put them back into logarithmic form. Because now what we see is that b to the power of qn equals m to the n. So remember, this to the power of this equals this. Do you see how this is saying the same thing as this? This one's just logarithmic and this one's exponential. B to the power of qn equals m to the n. Well, that's what we had here, okay? But don't forget, q is just log base b of m, right? That's where we started. Q is the exponent, b would need to become m. Log base b of m equals q. So I can think of this then as log base b of m to the n equals q times n, yes, but q is equivalent to log base b of m. And there we go, we basically have it. I mean, this is just written with the n on the left side. So we could rewrite that, right? Move the n over there. Instead of log base b of m times n, we'll do n times log base b of m, and then it really does look exactly the same way as on our formula sheet. And so there we go. Just by playing around with it a little bit, we proved that, yeah, if you've got an exponent on this m here, okay, you can bring it down and make it a multiplier on the whole log, and that is equivalent. So those are our 3 log laws. Okay, here's a little summary of them all in one place. They're all on your formula sheet. You don't have to derive them yourself, but it's always nice to understand why they work. Okay, we call them the product law, the quotient law, and the power law for logarithms, for obvious reasons. One's talking about multiplying inside the argument, dividing inside the argument, that's a quotient, and then a power inside the argument. Okay, and we can use these to massively simplify, to condense huge logarithmic expressions down to just 1 log, or vice versa. Take just 1 log and expand it out into many, maybe many smaller logs that are easier to evaluate, right? These can be super helpful for simplifying and making into logs we can actually solve, okay? A very important note, just like with our exponent laws, the base must be the same for the log laws to be applied, right? With our exponent laws, you couldn't say, a cubed times b squared. You can't say that's a to the power of 5, right? Or you can't say it's b to the power of 5. You can only do that if they have the same base. Then you can say it's a to the power of 5, right? This doesn't work. It doesn't even really make sense. So same thing for our log laws. We could simplify if we have log base 2 of 5 plus log base 2 of 10. We could use our log laws to combine those into log base 2 of 50. Do you see where that came from? Right? Log base b of m plus log base b of n is equivalent to 1 log with those arguments being multiplied. So I can multiply these two together inside one argument. 5 times 10 is 50, okay? But I could not do that if I had log base 2 of 5 plus log base 3 of 10. They have different bases, right? Same way our exponent laws can't really be applied if they have different bases. Our log laws can't be really applied if they have different bases. Just doesn't make sense, right? This is saying 2 to the power of something equals 5. This is saying 3 to the power of 10 equals, 3 to the power of something equals 10. Different bases, right? This one we can do it for, though. All right, let's try them out. They're kind of fun. I like log laws. All right, now right off the bat, I'm just going to mention there is very, very often multiple ways to approach it. Different relationships you might notice and apply first. So if at any point you're like, oh, I wouldn't have done it that way, it's totally possible that your way is correct as well, right? See it through to the end and see if you end up in the same place as me. I mean, these first couple are pretty simple, so there's really only one thing to do. But like as we get going more, there are actually multiple approaches you can take, okay? So don't panic if I notice something slightly differently than how you would have done it, okay? But let's go ahead. We're going to use the laws of logarithms to simplify the following expressions. So we've got log base 3 of 3 plus log base 3 of 2. Well, our product law of logarithms tells us that if we have 2 separate logs being added and they have the same base, which they do, we can combine them into 1 log where we're multiplying those arguments. So this is the same as log base 3 of 3 times 2. 3 times 2. In other words, it's log base 3 of 6. And there we go. We've condensed it into 1 logarithm. We've made it a bit simpler. Okay? Instead of being 2, now it's 1. All right. This one. Log base 2 of 15 minus log base 2 of 3. So we have 2 separate logs being subtracted. Our quotient law tells us, if we're doing that, we can rewrite it as log base b of those arguments being divided in 1 logarithm. So this is the same as log base 2 of, I'm doing log base 2 of 15 minus 3. log base 2 of 3. Always pay attention to the order, right? Order matters for division. N over m is a different result than m over n. Same thing here. 3 over 15 would be different than 15 over 3. So I need to do 15 over 3, right? M minus n gives m over n. So 15 over 3. And therefore, this is just equal to log base 2 of 15 over 3 is 5. And there we go. We've simplified, condensed, using our log laws. All right. This one. Okay, now, like I said, we could go at this all at once, okay? Or we could kind of break it down into a couple steps. I'll probably go just to take things nice and easy here at the beginning. Let's just break it down into steps. Let's just take nice little bite-sized pieces, okay? Now, one thing you might be noticing here is there's a 2, right? So a couple things you could do. You could rewrite this as like plus log 4 plus log 4, right? Just this part here, right? Because that's 2 log 4. And then you could combine it with the other ones. As is, though, like if you just leave this as 2 log 4, you can't really, like you can't multiply the 4 by the 10 because then you're ignoring the 2, right? You can't just say this is log 40, this part here is log 40, because then you're kind of ignoring the 2. So you could split it up into the 2 logs like that and then combine it that way. It's 10 times 4 times 4. Or what we could do is use our exponent law of logarithms, right? Our power law. We could take that 2 and make it an exponent on the 4. That's this one here. N log base b of m is the same as log base b of m to the n. So that might be what I do first. Again, if you notice something different and you approach it a different way, it's very possible your way is correct as well. There's multiple paths we can take through these. So just taking it nice and slow, one step at a time. This is the same as log of 4 squared. Okay, I might even go ahead and write a new line for squaring the 4. So this is log of 16. Okay, now again, we can just do this all at once. We'll have to be really careful. 20 is being divided by 10, and then we're adding log 16, so we need to multiply by 16. I might just take it a little slower here and just first combine these. So my quotient law says that if I have log base b of m minus log base b of n, I can rewrite it as a division of those two in one log. So this is the same as log of 20 over 10. And then I've still got this plus log 16. Okay. And then log of 20 over 10 is just log 2 plus log 16. And now I'm adding these two separate logs together. My product law tells me that I can multiply them inside one argument. So this is just log base 10, by the way, because no base was given. So it's a common logarithm assumed to have a base of 10. I can multiply them inside one argument, right? So log of 2 times 16 or log of 32, which we could actually do on our calculator because our calculator can handle log base 10. Couldn't do these ones on our calculator yet. We will learn the skills to be able to, but not yet because your calculator only works in log base 10. It doesn't have a log base 3 or a log base 2 button. The log button on your calculator is for base 10. Okay, but there we go. We just simplified those expressions using nothing more than our logarithm laws, right? Using those relationships to rewrite them in a simpler form. Okay, let's try these ones out. All right, so let's look at this one. Given that log base p of x equals 5, log base p of y equals 5, and log base p of z equals 6, we want to evaluate the following. Now, the problem here is we know what log base p of x and log base p of y and log base p of z are, but we have no idea what log base p of xy divided by z is, right? If we could make these show up in our equation, we could just put in their numbers and evaluate, because evaluate means like get a numerical answer, right? Figure out what this is actually equal to as a number typically. So how could we do that? Because I don't know what log base p of xy over z is. I only know what these individual logs of x, y, and z are. Well, maybe our log laws can help, right? Here we condensed them into a single log. I think here, if we did the opposite, if we expanded them, okay, that might be a good approach here. Because then I could break this up into a log base p of x, a log base p of y, and a log base p of z. So let's just look here. I've got log base p of x times y divided by z. So I'm multiplying these two, and then they're getting divided by z, right? So what do the log laws tell us? Multiplication, we can add those individual logs. Division, we can subtract. So again, just taking it a little bit, slow here at the beginning. Let's just first do the fact that we have log base p, I'm going to say xy, is being divided by z. So I can split these up like this. Right? That's just using the log laws. Okay? Division inside a single log, I can split up into two separate logs with subtraction. And then we can say, go a step further, log base p of xy, well, I'm multiplying inside that log, so that's the same as log base p of x plus log base p of y minus that log base p of z that was there from the beginning. Okay, and look at that. Remember, our problem was we didn't know what log base p of xy over z was. But we did know what log base p of x was. It was 5. We knew what log base p of y was. It was also 5. And we knew what log base p of z was. It was 6. So now we can take a look at this and say, all right, so this just equals 5. This just equals 5. So I've got 5 plus 5. And log base p of z just equaled 6. So 5 plus 5 minus 6. 5 plus 5 is 10, minus 6 is 4. So this expression evaluated is just equivalent to 4, right? Our log laws allowed us to do that. So sometimes students say, why would we bother expanding it? Doesn't that make it more complicated? Well, not necessarily if once expanded, the individual logarithms are more easily evaluated, right? And here it kind of, I know that seems a little bit cheap because I just happened to tell you about these, but sometimes you have something kind of, wild in here, but once you split it up, you realize, oh, these are actually kind of pretty easy to evaluate logs, right? It might be like 2 to the power of 4 versus some big multiplication and division inside the single log with a 2 and an x and all that stuff, okay? All right, let's look at this one here. Now, a very common student mistake. Do you think you can guess what the common student mistake would be here? Is to take the 2 and put it down. And they're thinking of this log law, so I like that they're thinking of that. However, the problem is the 2, that exponent of 2, is not on the entire argument, right? Right now, our argument is x y squared. It's not xy squared, it's x times y squared. So before we make use of that law, we would need to just have log base p of y squared. Then we could take the 2 down. So can I split this up into 2? I sure can, right? Because I'm multiplying x by y squared. So let's start there. This is the same as log base p of x plus log base p of y squared. And now I can use that power law of logarithms to bring the 2 down, okay? Now I can use this guy here to say that n can come down because the entire argument really is now to the power of 2 because I split it up into those 2 arguments, 2 separate logs in x and in y squared. All right, so this now is log base p of x plus 2 log base p of y. And look at that, we did it again because we know that log base p of y is just 5, and we know that log base p of x is also just 5. So this is just saying we have 5 plus 2 times 5. Or in other words, 5 plus 10. Or in other words, 15. So this thing ends up just simplifying and evaluating to be 15. And there we go. Kind of fun, right? I like these. So looking at the next one here, we want to rewrite log base 5 of 12 in terms of log base 5 of 2 and log base 5 of 3. So that in terms of means write an expression for log base 5 of 12 where only these appear. That's what in terms of means, right? When we write an equation in terms of something, it means that something is all that's allowed to appear in the equation. So how could we do this? How do we rewrite log base 5 of 12 as some combination of log base 5 of 2 and log base 5 of 3? Well, something that gives me a bit of hope is that we do have a way to take log base b of, a product and rewrite it as some individual logs. That seems kind of promising. If there were a way to write 12 as a product of 2 and 3, then we could use our log laws to rewrite log base b of 12 as some sum of, logs of 2 and 3. So let's explore that possibility. Well, 12, right? 12 is just, if we factor it, we could even do a prime factorization. 6 times 2, and 6 is just 3 times 2, right? So 12 is just 3 times 2 times 2. Hey! So log base 5 of 12 is equivalent to log base 5 of, 12 is just, we've now shown, 2 times 3 times 3, right? Now, why would we ever want to do this? Because again, now I can split this up into individual logs. So that's going to allow me to rewrite log base 512 in terms of log base 52 and log base 53. I'm multiplying them all together in one logarithm. So what do my log laws tell me I can do? I can split them up and add them as individual logarithms. So this is log base 5 of 2 plus log base 5 of 3 plus another log base 5 of 3, right? And there we go. We've written it in terms. All we were allowed to have appear was log base 5.2 and log base 5.3. Well, we've done that, right? That's all that appears. We could simplify this a bit more. Log base 5 of 2 plus, these are just like terms now, right? They're just numbers. Log base 5 of 3 is just equal to something, and I'm adding 2 of them together. So that's going to give me 2 of them. So this is plus 2 log base 5, 3. We could put that 2 up, but then it would kind of feel like it wasn't in terms, it would be, but it would be log base 5 of 3 squared instead of just log base 5 of 3. So I might just leave it like that. I think that's a little closer to what they were asking for. And there we go. Okay, we did it. All right, so use the log laws here. See if we can evaluate these without even using our calculator, right? We're actually going to be able to do that here. So 1/2 log base 5 of 25. Now, there's a couple things we could do here. You could recognize that log base 5 of 25 is just 2, because 5 to the power of 2 would equal 25, right? But that's no fun. Let's use our log laws. Just kidding. That's a totally valid approach. But since we just used our log laws, let's make use of them. So what we could do is bring that 1/2 up as an exponent, right? We could use this law here. Take the n and put it up on the m as an exponent, and that's equivalent based on our log laws that we spent some time proving. So that means this is the same as log base 5 of 25 to the power of 1/2. And 25 to the power of 1/2, hey, that's the same thing as the square root of 25, right? And hey, the square root of 25, that's just 5. And so now we've got this, log base 5 of 5. What's that equal to? Well, it's saying, right, 5 to the what power would equal 5, right? What exponent does 5 need to become 5? Just 1, right? Log base 5 of 5 equals 1. 5 to the power of 1 equals 5. So log base 5 of 5 is just 1. And there we go, we evaluated it. Notice we would have got the same thing using that method I was talking about at the beginning, because 5 to the power of 2 equals 25. So log base 5 of 25 is 2, and then 1/2 times 2 is 1. So see what I mean? Multiple approaches you can always take. Okay, now log base 7 of root 49 plus log base 7 of 49. Okay, now again, you're probably saying, well, root 49, that's just 7. Why don't I just write that as 7? You're totally right, but, let's try using our log laws a bit here, just to get used to them, to have some fun with them. Okay, but totally valid to just say root 49 is just 7. So this would just be 1, because I'd have log base 7 of 7. But let's try using our log laws a little more than that, just for fun. So this is log base 7 of 49 to the power of 1/2 plus log base 7 of 49. And then we could bring down our 1/2, right? So this is half of log base 7 of 49 plus log base 7 of 49. Well, log base 7 of 49, 7 to what power is 49? 2, right? So this is just 1/2 of 2 plus, same thing here, 7 to the power of 2 would equal 49. So log base 7 of 49 equals 2. Half of 2 is 1, right? 1/2 times 2 is 1 plus 2, so this equals 3. Is that the only way to do it? No. Is that even maybe the most obvious way to do it? Probably not, okay? But it worked, right? I mean, we could have actually done this probably a lot quicker if we had done what I said at the beginning. Root 49 is 7, okay? And then log base 7 of 7 would be 1. Log base 7 of 49 is 2, so 1 plus 2 would be 3. But again, there will be situations where the log laws are very helpful. I mean, we've already kind of seen that in some of these, okay? But just kind of getting used to these relationships here with some numbers that we're maybe a little more comfortable with at first. Using the log laws, the point of these is to see that using the log laws does give us the same thing as if we just maybe jumped in and didn't use the log laws. Okay. Let's try one from an old diploma, and then we'll take a little practice break. You can pause and try some practice. So for this release diploma question, we know that if log base 3 of 5 equals 3y, log base 3 of 4 equals 2x, and log base 3 of m squared equals 6, then what is log base 3 of 100 m to the 4th? Okay, what is it equivalent to? Now, the problem here is that we don't know anything about log base 3 of 100 m to the 4, but we do know stuff about log base 3 of 5. It's 3y. Log base 3 of 4 is 2x. Log base 3 of m squared is 6. And looking at our answers, we kind of want these like y's and x's and constants to show up in our result, right? And there's even a clue here. They're being added. So can we think of 100 m to the 4th in terms of things that are more like a 5, a 4, and an m squared, right? Well, let's think about that, because essentially our goal here, right, we do know stuff about these, so we're trying to make them show up in our equation. So how can we make 100m to the 4 look like those so that they show up in our equation? Well, first, let's just split up. We've got like constants, right? 5 and 4, and then m squared. So maybe I'll start there. Let's just split this up into log base 3 of 100 plus log base 3 of m to the 4th. Now, if your brain went in a different direction, that's okay. Like I said, there's often, pretty much always, more than one way to approach these, okay? But for me, I said, okay, I just want to split up the number part, the constant part, the coefficient, I guess, and the m part. Because now I can focus in and I can say, okay, 100, could I rewrite that in terms of 5s and 4s? Well, 5 times 5 would be 25, and 25 times 4 would be 100. So 100 is really just 5 times 5, 25, times 4. So let's do that. Log base 3 of 5 times 5 times 4, right? Not breaking any rules. 100 is 5 times 5 times 4. And then what about m to the power of 4? Well, hang on a sec. That's just m squared, right? Or m squared times m squared is m to the power of 4. Why would I do that? Because I know stuff about log base 3 of m squared. I don't know anything about log base 3 of m to the 4th, but I do know stuff about log base 3 of m squared. So what if I rewrote this as, instead of m to the 4th, m squared times m squared, which is equivalent, so I'm allowed to do that. That is just m to the power of 4, okay? Because now, look at this. Here's the magic part, I guess. Not magic, it's math, but right? Feels like magic sometimes because it's so cool. Log base 3 of, I can split these up. I have 5 times 5 times 4. My logarithm laws tell me I can write that as additions of individual logs. So log base 3 of 5 plus log base 3 of 5 plus log base 3 of 4. That's this one split up into 3 separate logs. And oh my goodness, I know what log base 3 of 5 is. I know what log base 3 of 5 is, and I know what log base 3 of 4 is, right? This is just 3y. This is just 3y, and this is just 2x. Okay, and then over here, I've got log base 3 of m squared times m squared. So that is just, once again, log base 3 of m squared plus log base 3 of m squared. Could have also written that as m squared squared and then brought the 2 down to get 2 log base 3m squared. That's actually, before I jump ahead and put in my 3y's, 2x's, and 6's, I might just combine some like terms here to make my life a little bit easier. So this is just log base 3 of 5 plus log base 3 of 5. Well, that's 2 log base 3 of 5's, right? Log base 3 of 4, only got one of those. And 2 log base 3 of m squared, right? Just combining like terms. Log base 3 of m squared plus another log base 3 of m squared just gives me 2 log base 3 of m squareds. Apologies, I ran out of room there. But now's the moment of truth. So 2 log base 3 of 5, well, that's just 2 times 3y. Or we could have done it here as well, 3y plus 3y, right? So this is 2 times 3y plus log base 3 of 4, that's just 2x. Whoops. Just going to keep my color coding going there for one more step. Okay, plus log base 3 of 4 is just 2x plus 2 log base 3 of m squareds, which I know is just 6. So plus 2 6's. And again, could have just gone ahead and said 6 plus 6 in that step, but just decided to combine the like terms there. Okay, so 2 3y is 6y. 2x is 2x, of course. And 2 times 6 is 12. So, oh my goodness, we did it. It looks like this matches answer B, 6y plus 2x plus 12. So all we needed to do was see if we could break this down into things that we knew about, right? So rethink of 100 expressed in terms of 5 and 4, and rethink of m to the 4th expressed in terms of n squared. Get those into individual logarithms because we know the values of those logarithms, and see what it simplifies out to. All right, so go ahead and give this one a shot. Of course, there's lots of practice kind of surrounding those questions that you can do as well, but at the very least, do this one while it's fresh in your brain, and I would recommend pausing for a bit and trying a few more to get a solid grasp on this, and then we're going to move forward into actually looking how we can solve exponential equations using these logarithms. All right, so we've seen, like, working with logarithms, right? We've seen how we can kind of use them to, like, rearrange exponential relationships, maybe get at some things that we couldn't tell right away when it was written in exponential form, or vice versa. When it's a log, we can rearrange into exponential and tell some stuff that we might not have been able to see when it was a log, right? So when we first started talking about logarithms, though, what we said, right, the claim was made that they were the inverse operation of exponentiation. Exponentiation, again, that's what's happening to x when I say something like that, right? We say x is being exponentiated, right? So that's an operation being performed on x in a sense, the same way, you know, x is being multiplied by 2. We could say x is being exponentiated to 5 in that one. So we made the claim, or at least I did, that we would eventually be able to apply them to both sides of an equation in order to undo exponentiation and determine an unknown in an exponent, right? The same way we would solve x plus 3 equals 5 by subtracting 3 from both sides, right? Because 3 is being added to x. So we could undo that by subtracting 3, right? If this was 2x, equals 8, we could do the inverse operation of multiplication because multiplication is happening to 2 or sorry, to x here, we could do the inverse operation of multiplication, division, and that would let us solve for x. And we kind of introduced logs as one of their main goals is allowing us to do that for this, because up until now we don't really have the inverse operation of exponentiation, right? We don't really have an operation that's the opposite of this that we could do to both sides and solve for x, the same way we could just divide by 2 here to solve for x, right? Well, now that we understand logs a little bit more, we are ready to start doing that. We are ready to actually do stuff to both sides and solve. So let's do it. Kind of exciting, right? So this is the exact same example that I showed in the notes when we first started talking about logarithms, and I kind of used it to point out we don't really know how to solve for x now, right? And now we do know how to solve for x because we understand logarithms. So what we're going to do, right, here, x is being multiplied by 2, so we divided both sides by 2 to undo that. Here, x is being exponentiated, so what we're going to do, since logs are the inverse of exponents, we're going to take the common log of both sides. We're going to take log of both sides. And what that gives us, if we just log the left side, we get log of 5 to the power of x. Log the right side, we get log of 100. Okay, which our logarithm laws now let us rewrite as specifically the fact that we have 5 to the power of x, right? If I use this law here, 5 to the power of x, I can take that exponent and put it down as a multiplier on the log. Okay, just like that. So this can become, I can take this x down, make it a multiplier on the log, and get x times log of 5. And there we go. We did it. We undid the fact that x was being exponentiated by taking the log of both sides, right? X is no longer part of an exponent. We now just have x times the log of 5 is equal to log of 100. And so there it is, right? We've now undone that exponentiation of x. X is no longer part of an exponent. And now, from here, we can just solve for x, because again, log 5 is just a number. Log 100 is just a number. We might not know its exact value off the top of our head, but we're just multiplying by x by some number, and that's equal to some other number. So since x is being multiplied by the log of 5, we can just divide both sides by log of 5. Inverse operation of multiplication is division, to get x equals log 100 over log of 5. Now, these are common logs. They're base 10. We took the log of both sides, so more often than not, it's going to make more sense to choose to take the common log, base 10. And the only reason for that is that our calculator, that log button on your calculator, is only set up to work for base 10 logs. Some of the newer calculators, you can change the base, but honestly, that's whenever we would want to do that. It's not really the type of question that would be helpful to solve that anyway, that way anyway, okay? But if we take base 10 log of both sides, our calculator can now just handle this. You can go to your calculator, maybe try it out just to get comfortable with entering logs on your calculator. Do log of 100, make sure you put the 100 in brackets or it's gonna think you mean log of 100 of log of 5, so close that bracket. But do log 100 over log of 5, and you should get that x is approximately 2.861631115. That's rounded. It's not an exact value, but approximately it's equal to that. And we can check our work, right? Check your work by plugging that back into what we started with. We said that we were trying to figure out what the exponent on x would need to be such that 5 to the power of x equaled 100. And if you do that, if you do on your calculator 5 to the power of 2.86 blah, 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 does it equal roughly 100? It does, right? So it works. We've solved for x when it was being exponentiated. All it required was for us to take the log of both sides, okay? Now, it's very important to remember the log button on your calculator only works for those common logs, those base 10 logs. So that log is not, it's not just log of whatever you want it to be, it's log base 10, okay? So for this reason, though we can technically take the log of both sides with any base, it usually makes the most sense to take the common log, base 10, of both sides. There are exceptions, like sometimes if if you take the log base 3 of something like 3, then you can just turn that into a 1. Log base 3 of 3 is just 1, since 3 to the power of 1 equals 3. But for the most part, when we're doing this log of both sides thing, typically log base 10 is the way to go. Not always, though, but most of the time. Okay, let's try this out with a couple examples. All right. So first up, we've got 3 to the power of x equals 25. Okay. Now, even without logs, we can kind of estimate the value of this. That's something that's often handy, if nothing else, just as a way to kind of check if your answer is reasonable in the end. But like we know 3 squared would be 9, and we know 3 cubed would be 27, right? So we can kind of estimate that x should be somewhere between 2 and 3, right? 3 cubed is too big. 3 squared is too small, so this exponent must be somewhere between 2 and 3, and probably closer to 3 than it is to 2, because we're at 25, which is pretty close to 27, which would be 3 cubed, okay? But now with logs, we can actually get a value for x without just that estimation, right? We don't just have to say it's between 2 and 3, probably closer to 3, okay? We can actually figure out what x is. So this is the power of logs, right? Before logarithms, we had no way to undo this exponentiation. Now we do, because logs are the inverse operation of exponentiation. They can undo this. So what I'm going to do, I'm going to take the log of both sides, right? If x was being multiplied by 2, we divide by both sides. X is being exponentiated, so we're going to take the log of both sides. I'm going to do log base 10 so that I can use my calculator. So I'm going to have log of 3 to the x equals log of 25. Okay, and now we can use our exponent laws to say that log of 3 to the x, I'm allowed to bring that x down and have it be multiplying the log here. So x log of 3 equals log of 25. And now, what's happening to x? It's being multiplied by the log of 3, so to solve for x, I would divide both sides by the log of 3. Divide by log of 3. And we get that x equals log 25 over log 3. Okay, and I'll just pull up the calculator here to show how to enter this, because logs are new to you as far as calculators go. So we wanted to do log of 25 over log of 3, right? So you can see right there, whoops, not that one. That's the natural logarithm. Okay, right there, sorry, hit the wrong button. Log, right? That is log base 10. Okay, make sure you're remembering that that's log base 10. It's not log of whatever you want, it's always log base 10. But to enter this, we would just do log of 25. I'm going to close that bracket. Otherwise, when I go to, if I go to divide now by log of 3, it's going to think I want to take the log of all of that, which I don't. I want to take the log of 25 and divide it by the log of 3. And then close that bracket and enter. So x would need to be approximately 2.93, right? To the nearest hundredth is what the question said. So 2.93 to the nearest hundredth, right? And hey, notice when we were checking our work, we said x should be somewhere between 2 and 3, and definitely closer to 3, because 3 to the power of 2 would be 9, which is quite a bit lower than 25, but 3 to the power of 3 would be 27, which is a little bit higher than 25, so it makes sense that x is a number between 2 and 3, and pretty close to 3, because this is slightly smaller than 3 cubed, but not by much. So our x is, well, the unrounded was 2.9299 or something like that. Okay, so our x to the nearest hundredth is 2.93. And there we go. Could always check our work, right? See what 3 to the power of that number we just got is. So I'll go second answer. 3 to the power of the answer we just got is 25, right? So it works. Okay, let's try this one out. So a slightly more complicated one, but still similar idea, right? We've got x is up in an exponent. We're never going to solve for x while it's up in that exponent, so logs might be helpful here. 5 to the power of x minus 2 equals 7 to the power of x plus 1, right? This one's a little, we couldn't really do the estimation thing we did here because, who knows, right? We could really think about it, but probably easier to just jump in and start taking the logs of both sides. So I'm going to take the log of both sides to work on getting that x out of the exponent, right? That's the first thing we'll deal with here. So I'm going to do log of 5 to the x minus 2, and that's equal to, take the log of this side, log of 7 to the x plus 1, right? Just like when x is being multiplied something, we divide both sides by that. Okay, here, X is being exponentiated, so we can take the log of both sides. Logs are inverses of exponents. All right, and now this is kind of often one of those things that comes in handy is that exponent law of logarithms, or the power law of logarithms, right? If I have x as an exponent in the argument of a log, I can bring it down and make that a multiplier. So be careful here. My exponent is not just x, it's x minus 2. So I can bring x minus 2 down and have that be multiplied here. That's going to give me x minus 2 log 5 equals, and then same thing here, but with the x plus 1. I can bring that x plus 1 down. So this now is x plus 1 times the log of 7. Okay, now, again, we're just solving for x, right? Remember, this is just a number. This is just a number. So we've solved equations like this before. It might, take a little more rearranging here and stuff, but we can get x by itself eventually. We've got two x's on either side of the equation. I think probably what I would do here is just actually expand this out. So multiply the x by log 5 and the negative 2 by log 5 and the x by log 7 and the 1 by log 7, because then I can have like all my x terms. I can focus on getting all the x's to one side, and then I can work on actually getting that x isolated. So let's just do that. I'm just going to multiply this out. So x log 5 minus 2 log 5 equals x log 7 plus 1 log 7, or log 7. Okay, and see what I mean? Now I can work on, right? If we had 3x minus 2 equals 4x plus 1, just making up numbers, right? We would know what to do, right? So don't forget log 5, just a number. 2 log 5, just a number, right? This is just a number times x. So what would we do back in, grade 7? We would bring all our x's to one side. Same thing here. Let's get all our x's to one side, and then we can focus on actually solving for them. So I'm going to do 2 steps in one if you're okay with it. I'm going to bring all my x terms to the left side. So I'm going to add 2 log 5 to both sides. Add 2 log 5 just to get rid of it here. And then I'm also, if you're all right with it, I'm going to bring the x over in the same step. So I'm going to subtract x log 7, subtract x log 7. Just being conscious of how much room I have left to write here, combining those 2 steps. So I'm going to have x log 5 minus x log 7, because I subtracted x log 7 from both sides. And the minus 2 log 5 isn't here because I'm going to add it to both sides. So now I'll have on this side the log 7 plus the 2 log 5 that I added to both sides. Okay, does that make sense? All right. And now look, okay, yes, we have 2 x terms over here, but what we could actually do, if these were just numbers, they are just numbers, but if they were just like a 4 and a 5, we would just subtract their coefficients, right? Combine like terms. That's essentially what we're going to do here, but it's a little tougher to do because, you can't just do log 5 minus log 7 in your head. But what we could do to just make things a little simpler is, notice they're both being multiplied by x, so we could pull out x as a common factor. Right, let's do that. I'm going to pull out x as a common factor. So if I pull an x out of x log 5, I'm just left with log 5. If I pull one out of x log 7, I'm just left with negative log 7. And that equals log 7 plus 2 log 5. And now, here we go. Almost there. X is being multiplied by log 5 minus log 7. So how do I solve for x? I divide by log 5 minus log 7. Right? That'll cancel it out on this side. What I do to one side, I must do to the other. Otherwise, the 2 sides of the equation aren't equal anymore. Okay, and here we go. Just barely ran out of room. But this means that x is log 7 plus 2 times log 2 log 5. The reason I said 25 is I was thinking, we could put that 2 up and make it log 25 if we wanted. Don't have to, though. Over log 5 minus log 7. And now we just need to, these are all base 10 logs, and it's said to the nearest hundredth. So we can just put it in our calculator and get the approximate value to the nearest hundredth. So log 7 plus 2 log 5, just going to break this up, log 7 plus 2 times the log of 5, okay, divided by, make sure you use brackets here. We divided by the log of 5 minus the log of 7. Okay, brackets there are important. Otherwise, what it's going to do is it's going to divide your answer by the log of 5, and then whatever that is, it'll subtract log of 7. But we don't want that. We want to divide by the log of 5 minus the log of 7, right? All of that's our divisor. And that gives me negative 15.35. Okay, so to the nearest hundredth, x equals negative 15.35. Okay, and again, we could check our work by putting negative 15.35 in here, right? So do 5 to the power of, I guess that would be negative 17.35, and then 7 to the power of negative 14.35, right? And see if left side equals right side. See if you get that that really is the value of x that would make, that would work for that equation. All right, one more here. Let's try it out. Actually, before we do move on to this one, just a quick note here. We could have kept simplifying this, right? I mean, I just chose to put it in our calculator there, but note that you could have done you could have brought the 2 up here, like I said, to make that log 25, and then you're adding those 2 logs, so you could use your log laws to combine those into a multiplication inside one log, and then you could combine these to log of 5 divided by 7, right? Combine those. Maybe we'll do that on this one to show that, probably would have been a good idea, honestly, to keep simplifying. Just makes our lives easier when it comes time to calculate. We don't have to put as much in the calculator. So let's move on to C here. Same thing again, right? Now we still have x being exponentiated. It's happening in a denominator here, though. So what we could do, we could work on simplifying this a bit or rethinking about it. We could write it as 5 times 8 to the negative x if we wanted, okay? But I might just jump in here and take the log of both sides. Okay, so log of 5 over 8 to the power of x. Just took the log of both sides. And then what we could do on this side, we could bring that x down according to our power law of logarithms. So this is x log 3. And then here, I might actually use that the quotient law of logarithms to split this up. Because right now, this is a little kind of tough to work with, right? So let's just rewrite that as log of 5 minus log of 8x, 8 to the power of x, sorry, right? That's just using that log m over n equals log m minus log n. I can split it up into 2 individual logs there. So that's all I did there. And now, okay, we're getting somewhere because I can bring that x down, right? Here I can bring that x down, and there we go. I've now gotten the x out of all of the exponents that it was part of, right? That's the purpose of logarithms. It allows us to get x out of an exponent, to unexponentiate, okay? All right, so now let me bring all the x's to one side. I'm going to add x log 8 to both sides. Add x log 8. That's going to give me x log 3 plus x log 8 equals, on this side, all we've got left is log 5. And then kind of a similar thing here, I've got, x times this plus x times this. So x is a common factor to each, so I can pull it out, right? Divide each of these by x and then multiply it by outside of the brackets to leave me with something simpler inside here. So I'm going to x log 3 divided by x just leaves me with log 3. X log 8 divided by x just leaves me with log 8, and that equals log 5. Okay, and now we can, since we're solving for x is being multiplied by this stuff, let's divide both sides by that stuff. So I'm going to divide by log 3 plus log 8. That'll cancel it out here, just equals 1. Log 3 plus log 8. And just barely ran out of room again. So I've got x equals log 5 over log 3 plus 8. Whoops, forgot not log 3 plus 8, log 3 plus log 8. There we go. Okay, and we could put this in our calculator now, but again, we could also just keep simplifying. So I could write this as log 5. I'm adding these 2 logarithms, so I could rewrite it as log of 3 times 8, right, which is just 24. So x equals log 5 over log 24. Common student mistake sometimes is to mix this situation here up with this situation. Be careful. We can't write this as log of 5 minus 24, right? That's not what this says we can do. If we have a division inside a single logarithm, we can rewrite it as two logarithms being subtracted, but it doesn't work the other way. Two logs being divided isn't the same as subtracting inside one log, right? That's not what the law tells us. So this is now all that's left to do. Since we want to the nearest hundredth, we would have to put it into our calculator, right? If it said exact value, we would actually kind of just stop there, because once we put this into our calculator, we're going to end up rounding. So log 5 over log 24, when I put that into the nearest hundredth, I got 0.51. And again, we can put it in our calculator because it's log base 10. We took the log of both sides, so we chose to take log base 10 of both sides. And that's the reason we did that, is that, well, now we can put it in our calculator and get it to the nearest hundredth. Okay, so go ahead and try at least this one out, but feel free to pause for a bit longer and try a few more and get comfortable with, solving for when x is in an exponent by taking the log of both sides. And then we will move on. All right, so whenever we have, like we've seen here, whenever we have that x in an exponent being exponentiated, taking the log of both sides mostly always works to solve for x, but we don't always have to. Sometimes there is, slightly more intuitive or quicker or not so calculator reliant way, okay? And we can do it without taking the log of both sides specifically when one base is a power of the other base, meaning that you have, in this example, for example, right, you have 2 to the power of x and 4 to the power of x minus 1. So what I mean by one base is just a power of the other is that 4 is actually just a power of 2, right? 4 is just 2 to the power of 2. 4 is just 2 squared, okay? 4 is just a power of 2, meaning that we could rewrite 4 as 2 squared, which means we could rethink of this equation as being 2 to the power of x equal to, yes, 4 to the x minus 1, but 4 is just 2 squared, right? So we could think of it as 2 to the power of x being equal to 2 to the power of 2 to the power of x minus 1. Well, why would we want to do that? Because now, look, we've got the same bases. And then our exponent laws, since we have 2 to the 2 being raised to the power of x minus 1, right? Whenever we have, x to the m being raised to a power n, we can rewrite that as x to the m times n, right? So we can multiply that 2 by x minus 1. So 2 times x is 2x. 2 times negative 1 is minus 2. So this is just 2 to the x equals 2 to the 2x minus 2. Now, look at this. 2 to the power of x is equal to 2 to the power of 2x minus 2. Well then, if that's true, what can we say about x and 2x minus 2? How could we raise 2 to something and then raise 2 to something else and have them be equal? Well, we couldn't. They must be the same thing, right? If 2 to the power of x is the same thing as 2 to the power of 2x minus 2, that can only mean that x is the same thing as 2x minus 2, right? You can't raise 2 to two different powers and get the same result. Those two things couldn't be equal. So x and 2x minus 2 must be equivalent. 2 is being raised to the power of x and to the power of 2x minus 2, and the result is equal. That's only possible if x is 2x minus 2. And there we go. So now we can just kind of write a new equation where we're just saying, well, x has to be the same thing as 2x minus 2. And this is definitely a very solvable equation, right? Now we're back in like math 10 or math 9 even. X equals 2x minus 2. We just have to solve for x. So let's add 2 to both sides. Gives me x plus 2 equals 2x. And then I'll subtract x from both sides to, gather all my x's on one side. And then so the x's are gone here. So it just tells me that 2 equals 2x minus x is just 1x. So x was just 2, right? We can check our work. 2 to the power of 2 is 4. 4 to the power of 2 minus 1, well, 2 minus 1 is 1. So 4 to the power of 1 is 4. 2 squared does equal 4 to the power of 1, right? 4 equals 4, so it worked. Okay, let's try it out. So we want to solve these exponentials by rewriting with a common base. So instead of taking the log of both sides, we're going to notice here that we have 2 to the power of x plus 1 and 8 to the power of x minus 3. And this is always worth at least checking because it can make things, a little quicker, a little simpler, and not as calculator dependent as taking the log of both sides. Sometimes it's unavoidable though. Like we can do it here because 8 is just a power of 2. 8 is just 2 cubed. So I could say 2 to the x plus 1 equals 8 to the power of x minus 3, yes, but 8 is really just 2 cubed, right? And I can do that here. Again, we can't always do it because 7, for example, in this one, that's not a power of 5. You can't rewrite 7 as a nice power of 5, right? I mean, technically 5 to the power of something does equal 7, but it's not a nice integer number, right? Same thing here. 3 and 25, right? 3 and 5/8 doesn't really work. But if both bases, like one is a power of the other, we can do that, okay? And that lets us solve this way. So now I have 2 to the x plus 1 using my exponent laws. I know I can multiply the 3 by the x minus 3. So this is 2 to the power of 3x. 3 times negative 3 is negative 9. And once again, if 2 to the power of x plus 1 is equivalent to 2 to the power of 3x minus 9, that's only possible if x plus 1 is the same thing as 3x minus 9, right? Raising 2 to those powers gave us the same thing. So those powers must be the same power. So now I just got to get all my x's to one side, right? Isolate x. We're back in math, very early math years. Well, early high school math years. Okay, so let's subtract x from both sides. That's going to give me, if I subtract x here, 2x minus 9. No, I'm not showing a ton of my work there, but does that make sense? Subtract x here to get rid of it. Subtract x on this side as well to give me 2x. And then add 9 to both sides. So add 9 to both sides to get 10 equals 2x. And then lastly, divide both sides by 2. And there we go. X equals 5. Can always check your work by going back and substituting it in and making sure it really does, solve the equation. Make left side equal right side. So 2 to the power of 6 is 64, right? If x is 5, 5 plus 1 is 6. 2 to the power of 6 is 64. And 8 to the power of 5 minus 3, so 8 to the power of 2, 8 squared, is 64. So yeah, 64 equals 64. X equals 5 is the solution to that exponential equation. All right, let's try this one out. 4 to the x minus 9 equals 1 over 64. Now, might not be as obvious, but 1 over 64, I mean, we know 64 is a power of 4, right? 64 is 4 cubed, because 4 times 4 is 16. Times 4 again would be 64, okay? So 64 is a power of 4, but we don't have 64, we have 1 over 64. So can you think of how to write 1 over 64 as a power of 4? Well, if 4 cubed is 64, what would be 4 to the negative 3? It would be 1 over 64, right? 1 over 64, I mean, you could look at it this way. This is 1 over 4 cubed, and 1 over 4 cubed is just 4 to the negative 3, right? When we have a negative exponent, we reciprocate, and the exponent becomes positive. So same idea here, but in reverse, right? Positive exponent, reciprocate, and the exponent becomes negative. And there we go, right? I mean, if we really wanted, we could rewrite these as 2 squareds, but why, right? Why bother? 64 is a power of 4, and so if 4 to the power of x minus 9 is equivalent to 4 to the power of negative 3, then x minus 9 must equal negative 3. So add 9 to both sides to solve for x, since 9 is being subtracted from x right now, and that gives us x equals negative 3 plus 9 is, positive 6. And could verify our answer. 4 to the power of 6 minus 9, well, that's 4 to the negative 3, which, hey, that is 1 over 64, right? So there we go. X is 6. All right, so here's one released from a diploma, okay? I'm going to show you 2 methods to go at this, okay? So I'll solve this 2 different ways because we could actually go with taking the log of both sides. We could also kind of play around with the exponential relationship and see if we can figure out, a common base here. So just goes to show again, there's multiple ways to approach many of these questions. So let's just take a look here. Given that y equals a to the x over a to the 2x minus 6, and that log base a of y equals x, where a is greater than 1, the value of x is, okay, so we want to solve for x. We're given two pieces of information about how x is related to y, right? So let's start out with this here. I'll kind of, like I said, I'm going to do this two different ways. So what does this tell me in terms of exponentials? Because again, I'm noticing like a to the power of x, well, this is kind of talking about a to the power of x as well, right? This to the power of this equals this. So this just means, this is just another way of saying a to the power of x equals y, right? So y is a to the power of x. Well, that means this equation, if y equals a to the power of x over a to the power of 2x minus 6, well, hang on a sec. A to the power of x is just y, right? A to the power of x is just y. So really this is saying y equals, because of this equation, right? We're essentially solving a system of equations here now. Y equals y over a to the 2x minus 6. Okay, and now if we kind of rearrange this a bit, if I multiply, let's just multiply both sides by a to the 2x minus 6. So a to the 2x minus 6 times y equals y. And the reason I did that is because I notice now if I divide both sides by y, I don't have to worry about the fact that I don't necessarily know what y is here yet, right? If I divide both sides by y, I get that a to the 2x minus 6 equals 1, right? Now hang on a second. A is being raised to some power, and the answer is 1. How can that be possible? What must this power be? What's the only exponent you can raise something to and get an answer of 1? It is 0, right? So this is just, right, we could say a to the 2x minus 6 is really just a to the power of 0, right? Whatever 2x minus 6 is, it must be 0, because when I raise a to that power, I get an answer of 1. So this lets us say 2x minus 6 must just be 0. And therefore, add 6 to both sides. 2x equals 6. Divide both sides by 2 because x is being multiplied by 2. And we get x equals 6 divided by 2 is 3. So x equals 3. So A. Now, is that the only way to approach this? Definitely not, right? There might even be other ways that I'm not showing you here, but I'll show you one other way. We could have actually just jumped in and taken the log of both sides as well. Okay, so let's do that. Let's just try it out. So if I have y equals a to the x, y equals a to the x over a to the 2x minus 6, right? And again, what would inspire us to take the log of both sides? Well, we do have an x in an exponent, right? And we know that when we have an x in an exponent, undoing exponents involves taking the log of both sides. The same way undoing multiplication involves dividing by both sides, we might be able to take the log of both sides here and get that x out of an exponent and solve for it. So normally, like I said, often what we would want to do is take log base 10 of both sides because then we can put in our calculator, but I'm actually going to choose not to do that here. The reason being, I know that log base a of y is x. So I know stuff about log base a of y. I don't know anything about log base 10 of y, right? This is a very algebraic one. They're not asking us to like calculate something to the nearest hundredth or anything like that. So what I'm actually going to do is I'm going to take log base a of both sides, right? We're doing it to both sides, so we can kind of pick what we want to do as long as we do it to both sides. So I'm going to do log base a of y equals log base a of a to the x over a to the 2x minus 6. Because, look at what I can now say. Log base
a of y, well, that's just x, right? This is just x. So x has to equal, and kind of same thing now. Now I don't have to worry about the fact that I don't know what y is, right? And now I can start thinking about log laws and how I can maybe simplify this a bit, because I've got log base a of a quotient, right? So I can use this law here to split it up into two individual logs. And that seems pretty promising in terms of simplification, because I'm going to be having a log base a of a argument, that contains an a, and same thing here, which means it probably will be pretty simplifiable. So I'm going to have log, if I split this up into two using my quotient logarithm law, I'll have log base a of a to the x minus log base a of a to the 2x minus 6. Okay? And we were right. Look, because don't forget what this is saying. This is equivalent to whatever exponent a would need to become a to the x, right? A to the power of what equals a to the x? Well, x, right? A to the power of x equals a to the x. So log base a of a to the power of x is just x. Alternatively, if you could get the same answer by saying log base a of a to the x, you could bring that x down, write this as x log base a of a. And what's log base a of a? Well, a to the power of what equals a? 1, right? So this is just x times 1, or x. See what I mean? Multiple kind of brain pathways you can follow to get the same result for these, okay? So now I've got x minus, all right, now same thing here. A to what power would give me a to the 2x minus 6? Well, 2x minus 6, right? Really what we're doing here is using log base b of b to the k is k, because b to the power of k equals b to the power of k, right? So same thing here. This is just equivalent to 2x minus 6. So x is equal to x. I'm subtracting both of those terms. So subtract 2x, subtract negative 6, so plus 6. Whoops, ran out of room there. Let me move up here. So now I've got x equals, let's just combine some like terms on that right side before we start actually solving x. X minus 2x is negative x plus 6. I'm going to add x to both sides to bring this x over to the left. That's going to give me 2x equals 6. And lastly, divide both sides by 2. And we get that x equals 3. Same result we got with our other method, right? So again, just goes to show there's multiple ways. Whatever jumps out at your brain, that might be a thread worth following, right? And you might diverge at different points and say, oh, I could do this or I could do that. You can ask yourself which one seems easier, which one am I more comfortable with, right? But often there is more than one way to approach this. When you look at your friend's solution, you might find they took a totally different path than you, but you still both got to the same destination. That's why these are kind of fun, I think. All right, so let's move on now to solving logarithmic equations. We just solved some exponential equations, but can we solve logarithmic equations? Okay, so what about when we have x being part of an argument of a log? We've seen that sometimes just rewriting it in its exponential form is enough, or playing around with it can be enough to solve for x, rearranging what the relationship is about. But sometimes that's not enough. We can still solve a logarithmic equation. There's basically two main strategies. They're essentially boil down to the same ideas, and both will always work, but often one will be easier than the other depending on the equation you're solving. And so when each term in the equation is a logarithm, in other words, everything is a log, like for example, a and b, you can kind of see here, everything is a log. Typically what's best then is to essentially use the laws of logs to make both sides of the equation a single log, right? We've seen how to condense multiple logarithms down into one log using our log laws, right? We can take addition of logs and turn them into the multiplication of arguments inside one log, or subtraction of logs and turn them into the division of arguments inside one log. So we can condense both sides just down to one log. And then if we have something, like log base b of x equals log base b of y, once we're done doing that, well, think about it. That just means x and y have to be equal. because we're doing the same thing to x as we're doing to y, and apparently the result is the same thing, right? Log base b of this is equal to log base b of that. Well, this must equal that then, okay? So that's one strategy. That works best when everything is a log. We can also, when some terms in the equations are not logs, like for example in C and D, you can see log, not a log, log, not a log, right? Sometimes then when that happens, it's often best to at least get all the logarithms together, combine all the logarithms using the laws of logs, and then you'll have something like, if you get all the logs together using your log laws, you'll have something like log base b of x equals the not a log is going to be on the other side, and then you can just convert to exponential form, and that can help you solve, okay? So again, both strategies can work, but sometimes one's easier than the other, and it just depends on what the equation is, okay? So go with, again, where inspiration strikes you. Now remember, this is important when we're solving logarithmic equations. We can get solutions without making any mistakes or doing anything wrong. We can get solutions that aren't actually valid, okay? And we call those, remember, an extraneous solution. So it's not actually a solution. We didn't make any mistakes in finding it, but it has to be rejected. Okay, and the reason is that the argument of a log cannot be negative. So along this process where we're kind of changing around the equation, we can end up finding values of x that might make, our later stages of the equation, it might solve those. But since we started with logarithms, those x's would actually have made our logs negative initially. Okay, so we will find some extraneous in these. I'll show you what I mean there. So just remember, you need to verify your solutions here. You always need to check that they would not make the argument of the log negative, okay, or 0. So if a value you find for x would make the argument negative, it's extraneous. So always check your solutions when solving logarithmic equations. Make sure you don't have any extraneous solutions. So let's start out. Solve for x in each of the following. Use the strategy that seems best suited to the equation. So looking here, okay, we've got log base 6 of 2x minus 1 equals log base 6 of 11, okay? Well, this one's actually a pretty easy one right off the bat because, look, if log base 6 of 2x minus 1 is the same thing as log base 6 of 11, well, then 2x minus 1 must be the same thing as 11. Right? How could log base 6 of this be the same as log base 6 of that if this and that aren't just the same thing? Right? So we can actually just say for this one, we can just say 2x minus 1 is 11. It has to be. Otherwise, log base 6 of 2x minus 1 couldn't be the same thing as log base 6 of 11. So if 2x minus 1 equals 11, we can solve for x, add 1 to both sides, because 1 is being subtracted. We get 2x equals 12, divide both sides by 2 to find that x equals 6. Now, what do we have to do? We must check to make sure that's not extraneous. Make sure it doesn't make the log argument negative, right? So verify that it doesn't make it negative. So 2 times 6 minus 1 is 12 minus 1 is 11, which is greater than 0, so it's a valid solution. Right? And you could extra check your work by actually, trying to calculate it out. But I mean, in this case, we can see, yeah, log base 6 of 11 does equal log base 6 of 11. So that seems like a pretty good solution. Okay, if it were negative, we would have to reject it. But in this case, that seems like a valid solution. Okay, so in this case here now, right, technically it was using strategy 1. Make both sides of the equation a single log. We just didn't really have to do anything because both sides of the equation already were a single log. Okay, let's try this one here. Log base 7 of x plus log base 7 of 4 equals log base 7 of 12. Now this one here, you'll see, right, we can't just say x equals 12 or 4 equals 12 because that's not true. Log base 7 of x plus log base 7 of 4 equals log base 7 of 12. But if we use our log laws here, you can see how this could become log base 7 of x times 4. And that would be the only thing on the left-hand side. So let's use that. Let's do that. Using our law of logarithms, right? Log base b of m times n just equals log base b of m times log base b of n, right? So I'm going this way. I'm saying log base 7 of x plus log base, whoops, sorry, is that a times? I meant plus, my bad, right? Log base 7 of x plus log base 7 of 4 is the same as log base 7 of x times 4, or 4x. And that equals log base 7 of 12. And now we're at the same place. Look, how could log base 7 of 4x be the same thing as log base 7 of 12 if 4x isn't the same thing as 12? Well, it couldn't be, right? So 4x must just be 12. And then divide both sides by 4, divide by 4. 12 over 4 is 3, so x equals 3. Now, I shouldn't put a box around that before I double check, but I think we're safe here because all we're taking the logarithm of is x, right? Or the only variable, I should say. The only log that involves our variable x is this one. And if x is 3, do we have any problems here? No, right? We're not taking the log of a negative number, so this is fine. X can equal 3. Okay. Let's try C here. All right. So taking a look here, we've got log of 8x plus 4 minus log of x plus 1 equals 1. So now everything isn't a log, so I won't necessarily be able to, do what we did here and get log base b of something equals log base b of something else and then show that those two must be the same thing. Although we actually could approach it that way. We'll have to get a little creative. I'll show you that when we get there. What we could also do, though, notice here, if I were to condense these down to one log, I would just have log base 10 of stuff equals 1. And then I could convert to exponential form and say, okay, so 10 to the power of 1 equals that stuff. And then solve for whatever x must be in that case. So let's go down that path, right? I'm subtracting these two logs. So remember, log of m over n is equivalent to log m minus log n. So I'm going to use that log law here. I'm going to rewrite these as one logarithm with their arguments being divided. So this would be equivalent to log of 8x plus 4 over, whoops, not log, x plus 1. And that would equal, that's the left side, that would just equal 1. Okay? And so now from here, what I could do, I could recognize, well, what's the base here? It's base 10, right? Because we didn't write it in. So this is the same as 10 to the power of 1 equals 8x plus 4 over x plus 1. So converting to exponential form, we get 10 to the power of 1 equals 8x plus 4 over x plus 1. And that's just an equation where the only thing we don't know is x, and we can solve for x. I just want to show you an alternate thing we could do to get to the same place. Might seem a little weird. Sometimes, though, this is a strategy that comes in handy. It can often be a good way to move forward. We could have also thought of this way. We could have thought of a way, if we wanted to kind of use this strategy, the one we used in A and B, we could have tried to figure out a way to write 1 as a log with a base 10, right? Because that would have both sides being a log with a base 10. So how could I do that? How could I rewrite, here, or we could have said log base 10 of 8x plus 4 over x plus 1. Well, 1 is equivalent to log base 10 of 10, right? Because 10 to the power of 1 would equal 10. So log 10 is just 1, right? And so we've rewritten 1 as log of 10, and now we kind of turned this into a similar situation to A and B. I have log base 10 of this stuff equals log base 10 of 10. And therefore, this stuff, 8x plus 4 over x plus 1, must just equal 10, right? If log base 10 of this equals log base 10 of that, then this and that must be the same thing. Notice we got to the same place. 10 to the power of 1 is just 10. So another way to approach it. Sometimes that strategy of thinking of a way to rewrite a number as a log can come in handy for certain questions. So I just did want to point it out. But either way, we're now in the same place. We have that 10 equals 8x plus 4 over x plus 1. And now I want to solve for x. I think what I'll first do is let's just get all our x's out of denominators. So I'll multiply both sides by x plus 1 to get these out of the denominator. X plus 1 over here. Probably go ahead and distribute. So I'll do 10 times x, 10 times 1 to get 10x plus 10 equals 8x plus 4. And now it's just a matter of getting all my x's to the same side and isolating it. So I'm going to subtract 8x here, subtract 8x here. 10x minus 8x, that'll leave me with 2x plus 10 equals 4. And then subtract 10 from both sides, and we're almost there. Subtract 10, and I've just got that 2 times x equals 4 minus 10 is negative 6. And divide both sides by 2. Well, we might be safe. Let's see. X equals negative 3. Okay. Now, remember, it's okay there's nothing wrong with just x being negative. What would be a problem is if x made our argument negative overall, okay? And in this case, I actually think it will, right? Because look, if we verify or check our solutions, I guess it's not really verifying, but checking them, just making sure they're not extraneous, right? 8 times negative 3 plus 4, negative 24 plus 4 is negative 20. That makes the argument of our logarithm negative, right? If you try to do log of negative 20, it's going to say error, right? It also makes this one negative. Negative 3 plus 1 is negative 2. Now, all it takes is for it to make one of them negative, right? In this case, it does make both arguments negative, but it's not like, if it made one of them positive, it would be fine, okay? So this is definitely an extraneous solution, right? Negative 3 plus 1 is also negative 2. So this is extraneous. Well, that's the only solution we found, and it's an extraneous solution. So this actually just has no solutions, right? There's only one solution we could find, and it ended up being an extraneous solution. So there's actually no value of x that could make this equation true. It has no solutions. So reject it, right? This is a extraneous solution, and therefore, since that's the only solution we had to choose from, and it wasn't actually a valid one, this has no solutions. All right. So don't forget to check your solutions to see if they are extraneous. And what makes them extraneous for a log argument? Again, the reason we found that is because we kind of slightly changed the equation when we moved here, when we got rid of our logarithms. So while negative 3 does make 2x plus 10 equal 4, for example, it still can't go into this equation where we had logs involved, which is what we really started with. We ended up here and we didn't break any math rules or do anything wrong, but we kind of changed the equation by getting rid of our logs, and therefore we open up the door to finding solutions that don't actually work with what we started with. Okay, here's another one where we've got, log stuff and non-log stuff. So again, multiple ways to approach. But typically when we have logs and non-logs, we basically want to get it to look something like this, right? Because then we can just say, all right, log base b of x, log stuff equals non-log stuff, and then we can do our, this to the power of this equals this, and get our solution that way. So let's try that out here. I'm adding these two logs. So the product law of logarithms tells me I can do this. I can multiply inside a single logarithm. This is the same as log of x times x minus 15, and that equals 2. So this gives us log of x times x is x squared, x times negative 15 is negative 15x, and that equals 2, okay? And here we go. We can now convert to exponential form because this is just saying 10 to the power of 2 equals x squared minus 15x. So 10 squared equals x squared minus 15x. Or 100 equals x squared minus 15x. Again, I'll also just show you that because it does sometimes come in handy, right? We could have also said log x plus, well, here, I'll still combine those two. We could have said log of x times x minus 15. And we could have tried to think of a way to do it like a and b, where we make both sides log base 10, okay, and then just drop the logs all together. How could we write 2 as an equivalent logarithm in base 10? Well, log base 10 of what would equal 2, right? That's what we're essentially trying to figure out. What needs to go here to make log base 10 of something equal 2? Well, 10 to the power of 2 is 100. So log base 10 of 100 is 2. So we could have done this as well. Log base 10 of 100, right? We're not breaking any rules. 2 is just log base 10 of 100. And so now we can see if log base 10 of this equals log base 10 of that, this must equal that. So we could just say x times x minus 15 equals 100. Or x squared minus 15x equals 100. And notice we're in the same place, right? So multiple ways we can approach these, multiple things we can think about. Anyway, let's move on with this one. This is a quadratic, but we know how to solve quadratic equations, right? We've been doing that since Math 20. We've got 100 equals x squared minus 15x. Remember, whenever solving a quadratic, we know we're going to have to factor this, or maybe even use the quadratic formula. And in both cases, for the quadratic formula, we need to have everything on one side, and for factoring, it's much, much easier if everything's on one side. We always want to start from, whenever solving a quadratic equation, we want to start from stuff equals 0. Right? So I'm just going to subtract 100 from both sides, subtract 100 from both sides to give me that x squared minus 15x minus 100 equals 0. Swapped the left and the right side there. That just feels a bit better for some reason. Okay. And now if I can factor this, right, this is why we want stuff equals 0, because I'm looking for two numbers that multiply to negative 100. Add to negative 15. How about negative 20 and 5? Remember, when in doubt, you can just factor this 100 out and look for matches that would also add to negative 15. But I think negative 20 and positive 5 would work here, right? Negative 20 times 5 is negative 100. Negative 20 plus 5 is negative 15. Okay, so those two work. So this gives me x, those two factors, this must be equivalent to x minus 20 times x plus 5, right? And that equals 0. This is why we always want to have stuff equals 0, because it's really easy now to figure out, how do I make this factor times this factor equal 0? Well, the only way to multiply two things together and get an answer of 0 is if one of them is 0, right? So if this is 0 or if this is 0 is now the only way we know how to make that equation true. If we don't have stuff equals 0, it's a little harder because it's not just, oh, make that equal 0 and make that equal 0. You got to think a little more about how to make it multiply to some non-zero number. Okay, that's the idea behind bringing everything to one side. Okay, again, you could always check your work on the factoring by foiling these back out and making sure it's equivalent to that. But this tells us then that, okay, so x minus 20 times x plus 5 equals 0. Well, that can only be true if x minus 20 equals 0. So if x equals 20, or if x plus 5 equals 0. So if x equals negative 5. Okay, and so those are my two solutions. But what do I need to do before putting a box around them? Right, I need to verify that they're not going to make my arguments negative, right? So x equals 20, let's check that. We would have log of 20 plus log of 20 minus 15, which is positive 5. So this one's safe. This one's valid, right? This is a valid solution. Okay, we've just checked that it doesn't give us any problems. Let's check this one, negative 5. Oh, right off the bat. Log of negative 5, nope, we're done. Okay, even if it left this one positive, we'd still be done. It would be an extraneous solution, but it also happens to make this one negative 2, right? Negative 5 minus 15 is negative 20. So no, this one definitely extraneous. Makes arguments negative, so this is an extraneous solution. Okay, so our only solution to this is actually just x equals 20. Right? And you could double check your work. These are even log base 10, so you could even use your calculator to check your work. Try log of 20 plus log of 5. See if it equals 2. It will. Okay, so go ahead and try, actually, we could quickly look at that. I'll just show you, right? Log of 20 plus log of 20 minus 15, does it equal 2? This is just verifying our work, right? Let's see. Well, this is log 20 plus log 5. Does that equal 2? Well, log of 20 plus 5 is log of 20 times 5, or log of 100. And hey, sure enough, log of 100 is 2, right? Because 10 squared is 100. So, quickly verified our work. Didn't even need the calculator. The reason I went back is I said you could even use your calculator, but I wanted to show you don't even need the calculator to verify that one. Algebraically, we can see it pretty quickly. Okay, now go ahead and try this one out. As always, right, there are definitely more practice questions that are probably worth taking some time to get comfortable with, but at the very least, do this one while it's fresh in your brain, and then if you want to keep watching the video lesson, you can. But take a little practice break, take a break from my voice, try out some to get the hang of this. All right. All right, so there is one more formula we can use. It is on your formula sheet. It's called the change of base formula. As the name suggests, it lets us change the base of a logarithm. Why would we want to do that? Well, remember, the laws of logarithms only work if all of the logs have the same base, right? For example, log base 2 of x equals log base 4 of 5 cannot be solved as is, or at least easily, because one has a base of 2 while the other has a base of 4, right? So we can't do what we were doing in those previous examples and say like, oh, x equals 5 because they have the same thing happening to them. They don't. This is a log base 2. This is a log base 4. Right? So there's not much we can do with that right off the bat. However, we do have what's called the change of base formula, which allows us to express any log to the base of our choosing. So if we wanted to convert log base b of c, just keeping it general for now, to an equivalent log base a of something, right? What would we need to do if I wanted to change this from being a log base b to being a log with base a? I can use this formula here. So it looks a little weird at first, but all it's saying is that if you want log base b of c, and you want to change that from something in terms of a log base b to something in terms of a log base a, here's what you do. You take log base a of the argument over log base a of the base. Okay, that's actually it. So I just look at it as like take log base, whatever you want to get it to, of c over log base, whatever you want to get it to, of b. This is especially handy when we want to like check our work with a calculator or something, because then we can turn any log into a log base 10, for example, and do it on our calculator. Now, that's not going to help us if we need exact values, but it's a nice way to check our work, for example, right? For example, here I could do log c over log b, right? Log base 10 of c over log base 10 of b. A quick proof of why this formula makes sense, okay? It's just kind of using, I've already kind of written out the proof here, but let's just say we start with log base b of c. How can we show that it's equivalent to log of base some different base of c over log of base a of b, right? Over some log of some different base of b. How can we show that? Well, we'll start out, we'll just say let log base b of c equal y. Y just being whatever log base b of c happens to equal, okay? And then we can write that in its exponential form, so b to the y equals c. And now, again, when we're coming up with formulas and looking for relationships, sometimes we kind of just try stuff and see if we can find anything. So what I did here is I took log base a, some different base than what we started with, of both sides. Log base a of b to the y equals log base a of c, right? That's all I did, took log base a of both sides. Well then, by the power law of logarithms, I can bring that y down, and we see then that y times log base a of b equals log base a of c, and then dividing both sides by log base a of b, I get this, y equals log base a of c over log base a of b, starting to look familiar, okay? But don't forget, we said at the very beginning, y is just what we were letting log base b of c equal. So log base b of c is equivalent to log base a of c over log base a of b. And again, a can be whatever we want, right? If we have some log that's with a base we don't like for whatever reason, now we can rewrite this in terms of some log that we do like, some base that we do like. So we could use this to rewrite, for example, well, let's just jump into it because it's the same example we had here, or a similar one anyway, right? If I had log base 2 of x equals log base 4 of 5. Now we can solve this because with the change of base formula, we've actually got options. I could either rewrite this in terms of log base 4s, or I could rewrite this in terms of log base 2s so that they both have the same base. Okay, so using our change of base formula here, two options. I could express log base 2 of x as an equivalent log with base 4. Right? So all our change of base formula says, if I want to turn this to a log base 4 thing, I just have to take log base 4 of x over log base 4 of 2. So log base 4 of x over log base 4 of 2. And then we can solve using that change of base formula. So here's what I did. Log base 2 of x equals log base 4 of 5. Can't solve it like this because different bases, right? But if I rewrite this as log base 4 of x over log base 4 of 2, that is now all in terms of log base 4s, right? And now I just need to solve for x. So log base 4 of 2 is actually just 1/2 because 4 to the power of 1/2 equals 2, right? The square root of 4 equals 2. So this is, I'm dividing by 1/2. That's the same as multiplying by 2 over 1. So 2 log base 4 of x equals log base 4 of 5. And then log base 4 of x squared equals log base 4 of 5. So there we go. We got it to the point where we had log base 4 of stuff equals log base 4 of other stuff, right? And so if log base 4 of x squared equals log base 4 of 5, then x squared equals 5. That's the step that wouldn't have been possible if they had different bases, or at least it's one of them, and now they do have the same base. Okay, another approach we could have taken here is back at this part. We could have multiplied both sides by log base 4 of 2, although that would really just lead us to the same place in the end, I guess. Okay, and so taking a look here, right, if x squared equals 5, that means x equals plus or minus root 5. And since the argument can't be negative, and we have log base 2 of x, we would reject the negative root 5. It would just be root 5. Okay, but we also could have done it the other way, right? Two different bases. If we can get them to be the same base, we can solve. So we also could have done, right? Here we turned the log base 2 into something in terms of log base 4, but we could have gone the other way. We could have turned the log base 4 into something in terms of log base 2. Our change of base formula lets us change any base into any other base. So log base 4 of 5 could be written as log base 2 of 5 over log base 2 of 4, right? And then similar process, log base 2 of x now equals log base 2 of 5 over log base 2 of 4, right? Log base 2 of the argument over log base 2 of the base. And then log base 2 of 4, well, that's just 2, because 2 to the power of 2 would equal 4. So we have log base 2 of 5. Chose here to multiply both sides by 2, so 2 log base 2 of x equals log base 2 of 5. Now, I can't quite drop the logarithms yet, because I don't have log base 2 of x equals log base 2 of 5. I have 2 times log base 2 of x. So what I can do, though, bring that 2 up there as an exponent, and now I really do have that, right? Log base 2 of x squared is equal to log base 2 of 5. So x squared must equal 5, and therefore x is plus or minus root 5, but for the same reasoning, we're taking the log of x. We can't take the log of a negative, so we have to reject the negative root 5. So our solution then is just positive root 5. Same answer, approaching it two different ways, turning the log base 2 into log base 4s versus turning the log base 4s into log base 2s, so that both are in the same logs. And if there's no variables involved, if there's just like numbers, we can even use the change of base formula to make all logs base 10, and then evaluate using our calculator, because our calculator can do log base 10, right? So this makes the change of base formula especially powerful. If you change logarithms to base 10, you can always use your calculator to evaluate. Now again, this often doesn't work because we often want like exact values or simplifications, so it doesn't often work as a final answer when we need exact values, but at least it's a great way to check your work, right? So it says, use the change of base equation to evaluate each expression using your calculator, round to the nearest hundredth. Now our calculators can't do log base 5, but they can do log base 10. So what we can do here is rewrite this, okay? How could I use the change of base formula? Well, again, all the change of base formula says that log base b of c can be written in terms of log base a by doing log a of the argument over log base a of the base. Okay, so if I want to turn this to base 10 so that my calculator can do it, I would need to say, all right, this equals log base 10 of 10 over log base 10 of 5, which now our calculator can do, right? So if you put that in your calculator, log 10 over log 5, what do you get? I got, what did it say to round to? The nearest hundredth. So I'll do 1.4307, but to the nearest hundredth, that's 1.43. Okay, or I guess I should say it's approximately equal to 1.43. And there we go. We just used the change of base formula. Okay, look at these. We have 3 different logs, all with different bases. I definitely cannot use my log laws here, right? Be careful. Always check the base. Sometimes students will jump in without thinking, and they'll say, oh, this is log base 4 of 9 over 7. No, it's not, because this is log base 4. This is log base 6, right? You've ignored the 6, and we can't do that, right? Same way the exponent laws can't be applied if you have different bases, right? You can't say that x squared times y cubed is x to the 5 or y to the 5, right? That doesn't make sense, okay? It's the same thing here. Different bases, we can't use our log laws. But we could change them so that they all have the same base. That's one option. And in this case, since it told us just to use the change of base equation to evaluate each expression using our calculator, let's just change them all into base 10. Okay, so what is this then? This is going to be, if I want to use the change of base formula, right? If I want base 10, I'm going to have to do log base 10 of 9 over log base 10 of 4 for this one. Again, I can leave out the base if it's a 10 because that's assumed. Log 9 over log 4 minus, this one will be log 7 over log 6. Now this one, I got to be careful here because what about that 3, right? I mean, what we could do actually is do 3 times log 4 over log 2. We could also, if we wanted, have put that 3 up, make it a 64, and then do log 64 over log 2. Same result in the end either way. So now calculating this out, log 9 over log 4 gives me 1.58496 minus log 7 over log 6 is 1.08603 plus 3 times log 4 over log 2. Log 4 over log 2 is just 2. That actually makes sense. I don't know why I didn't need to use the change of base formula there, did I? I wasn't thinking. Of course, 2 to the power of 2 is 4. So this was just 2 to begin with. Whoopsies. All right, so now we just got to add those together. So 1.58496 minus 1.08603 plus 3 times 2 is 6. So that gives me 6.49893, or to the nearest hundredth, which is what it asked for. Be careful, not 6.49, right? You'd hate to do all this correctly on the diploma and then end up not getting the mark because of rounding. So this should be 6.50, right? That 9 rounds up. It's like 9 is rounding up to a 10 essentially, or 49 is rounding up to 50, right? So 6.50 is what I got to the nearest hundredth. All right. And so while that's not, the only use of the change of base formula, I don't want you to think it's just for putting it into your calculator. That is one of the nice ways we can kind of use it, is to get it into base 10 so that we can more easily enter it, right? But like we saw here, it can also just be used for solving equations algebraically, right? I didn't pull out the calculator here at all. Okay, so the last thing we're going to talk about here for this lesson is just some real-life applications of logarithms. Again, nothing different in terms of skills. It's just real-life things that often pop up with
that are logarithmic that you've actually probably heard of and didn't realize they were logarithmic, or maybe you did. But either way, let's talk about them here. So many measurement systems you have used. I know if you've taken chemistry, you've used one of them for sure. If you've taken Science 20, you've also talked about one of them, right? I mean, even if you just took Science 10, which I'm assuming you did if you're now in Math 30, okay? You have talked about a logarithmic scale. The pH scale, for example, is logarithmic. Okay, so many of these measuring systems use logarithmic scales. A lot of them involve, right, for example, the pH scale, it involves measuring some like real physical quantity, some what's the word I'm looking for? Tangible thing, and then taking the log of that measurement. Okay, why would we do that? Well, it's really convenient when there is a huge range in values to be rated, from very tiny up to enormous, okay? So I'll use the pH example because that's one like you're probably the most familiar with as a high school student, right? But these other ones are as well. We'll talk about them. The pH scale, what does it measure? If you've taken Chem 20, you would have learned that it measures the hydrogen ion concentration. Right? Now, the problem with measuring something like this is that if we just like use the hydrogen ion concentration, it becomes ridiculous the range of values we have to cover for just like the normal chemicals that you would find in your cupboard or your kitchen, right? And so it becomes kind of a silly scale without logarithms because we have like times 10 to the negative 14 all the way up to like things that are times 10 to the 1. Like that's such a big range of values. We have tiny values all the way up to enormous. And so logarithmic scales allow us to more conveniently do that because you know that the pH scale more or less goes from 0 to 14. It's technically possible to go beyond those, but that's the most chemicals fit within 0 to 14. Most concentrations do, right? But again, you learn in chemistry that like this is actually a huge range of ion concentrations, right? You measure the hydrogen ion concentration, it can be as low as like times 10 to the negative 14 for water, or well, that's just 10 to the negative 7 for water, sorry. 10 to the negative 14 for strong bases, and then big numbers like even up to like 1 mole per liter for strong acids. Sorry, that should go down here. Bases are up here, of course, okay? So what this does, why logs let us measure a huge range of values in a more convenient way, is because of, well, think about this. What's log of 1? It's 0. Log of 10 is 1. Log of 100 is 2, right? 10 to the power of 2 equals 100. Log of 1,000 is 3. Log of, let's jump up now, log of 1 billion is 9. It's just 9 because 10 to the power of 9 is a billion. And do you see what I mean here, right? Look at the huge range of values. If we were measuring something, right, actually taking some physical measurement, and our measurements ranged from 1 up to a billion, that's a big range of things to cover. And our scale would start to feel kind of silly if we're saying, okay, it goes from, 1 all the way up to a billion, and then there's all this stuff in between, like, 10 would be like way down here, barely visible. 100 would still be barely visible compared to a billion, right? But if we take the log of those measurements that have a huge range of values, look what our scale becomes, right? But we have to recognize then that that means a jump of 1 on this logarithmic scale really means the measurement got bigger by a factor of 10, right? A jump of 2 means it got larger by a factor of 100. A jump of 3 means it got bigger by a factor of 1,000. And a jump of 9 means that measurement actually got a billion times larger, okay? So some of the real life ones that use logarithms, the decibel scale for measuring sound, right? You've heard of things like, a concert is however many decibels, okay? What that does is it takes the log of the sound energy being released each second. So that can have a huge range of values, from very small amounts of energy to huge amounts of energy. And so if we take the log of it, we can make a more convenient scale. The Richter scale for measuring earthquakes, that takes the log of the kinetic energy carried by the earthquake. So have you heard of like a 5.4 magnitude earthquake versus like a 7 magnitude earthquake, right? That's actually a logarithmic scale. What you're hearing when you hear like a 5.1 scale earthquake is the log of the amount of energy that was released, okay? The pH scale, as we talked about, measures the acidity or basicity of chemicals, and it takes the log of the hydrogen ion concentration, because that's what determines a chemical's acidity or basicity. So all three of these, and most of these, use common logarithms. And if we think about that, that means, like we said, that a change of 1 on the scale corresponds to 10 times greater or smaller actual measured values. Because again, log base 1 of 0, log base 10 of 10 is 1, log of 100 is 2, log of 1,000 is 3, right? So this is what the scales are like given to you as. But the physical measurements that they're actually measuring are these, right? So if an earthquake releases, 10,000 joules of energy, we might say it's a magnitude 4 earthquake. Okay, and notice what that means though. When you hear like a 3 earthquake versus a 4 earthquake, it doesn't sound that much worse, does it? Right? But it's actually 10 times more energy, right? So again, you probably would have talked about this in chemistry class. A decrease of 1 on the pH scale actually corresponds to an acid that is 10 times stronger. So like something having a pH of 4 versus a pH of 5, it doesn't sound like it's that much more acidic, does it? But because that's a logarithmic scale, it's actually 10 times more acidic, right? And a decrease of 2 on the pH scale actually means that the acid is 100 times stronger, right? Because we're going from log of 100 to like log of 1. So something with a pH of 3 versus a pH of 5, that actually means it has 100 times stronger acidic hydrogen concentration. Okay, a difference of 3 means the acid is 1,000 times stronger, etc., etc. So like an earthquake, to use an earthquake an example. If an earthquake with a Richter magnitude of 6, it's actually 10,000 times more powerful than one with a magnitude of 2. Because again, the difference between those, it's a logarithmic scale. So we're saying the log of something equals 6 and the log of something equals 2 when we're talking about those Richter magnitude scales, right? So since the difference between the logs is 4, the actual measurement, right, it's 10 to the power of 4. It's 10,000 times stronger, right? So that kind of shows you, right? Like a Richter magnitude of 7 doesn't sound that much worse than 6, but it's actually 10 times more energy being released because it's a logarithmic scale. So let's try an example here. Again, you're going to notice it's the same math skills, right? We're just talking about some real stuff now. So Joy listens to her radio at a sound level of 60 decibels. She attended a music concert that had a sound level of 125 decibels, right? And you might think, okay, so the concert was about twice as loud, right? About twice, a little more than twice as loud, a little more than twice as much sound energy being released. Because this is a logarithmic scale, we'll find that that's actually not the case. So, determine how many times more intense. You may use the formula, the decibels are equal to 10 times log of I over I naught. I naught is how we would say that, where beta, that's the symbol beta, beta is the decibel measure. It's logarithmic. I is the actual intensity of the sound, and I naught is just a constant. That comes up in this formula. It's just a constant. It's the minimum sound intensity that a person can hear. Notice they didn't give it to us. So it is just some number, but they didn't tell us what it is. That kind of implies we don't need it. Okay, so let's just see how this goes without knowing that I naught. Now, it asked us how many times more intense is the music concert than the radio, right? Well, if we think about that, right, how do we figure out how many times more, right, in general? Like if I have $100 and you have $50, how many times more money do I have than you? Well, I have twice as much, right? How did you figure that out? You took 100 and divided by 50, right? If I have, $45 and you have $15, I have 3 times as much money as you because 45 divided by 15 is 3, right? 15 goes into 43 times, so I have 3 times as much money as you do. Okay, so that's all it really means when it says how many times more. We just need to divide, and we want to know how many times more intense was the music concert
than the radio. So we need to take the intensity of the music concert and divide it by the intensity of the radio. So music concert by radio intensity. Okay, so let's think about these each individually, because yes, we need to divide the intensity of the music concert by the intensity of the radio, but we don't even have an expression for that yet. So let's just think, can we solve for the radio intensity? If we can do that, then we can divide the music concert intensity by it. So for the radio, we were told it has 60 decibels. That's its decibel measurement. So 60, just plugging into this formula here. Actually, let me do this. The decibel rating will be 10 times log of I over I naught, which we don't know what that is yet. But that means that for the radio, 60 equals 10 times the log of whatever, I'm just going to use an R to represent radio, whatever the radio's intensity is over I naught. So solving for I radio, right, if I divide both sides by 10, that's actually why we call it a decibel. Deci means 1/10 of a bell. It's that 10 in the formula. Divide by 10. So 60 over 10 is 6. So 6 equals log of I radio over the threshold intensity. Okay, and look at this. We've now got a log base 10 of something equals 6, right? So notice here, this is now, we can just convert this to exponential form to start solving for I radio. So 10 to the power of 6 is I radio over I naught, that kind of reference intensity, right? And therefore, the radio is just equal to a million, 10 to the 6 is just a million, I'll leave it as 10 to the 6 because that's more convenient to write, times that reference intensity. Okay, now again, we don't know the reference intensity, but if we think about where we're headed here, we're going to end up dividing this, we're going to end up dividing the concert by this. The concert's also going to include that. So I have some hope here that these might cancel out. So now let's do the concert's intensity. It's going to be honestly the exact same process. It's just a different number that we're putting in. So the concert sound level was 125 decibels. So that's equal to, using our formula there, 10 times the log of, and I'll use a C, IC, to represent concert, over the reference intensity I0, or I naught. And then same thing, divide both sides by 10. So 125 divided by 10 is 12.5, equals log of the ratio of the concert's intensity to that reference intensity, I naught. Okay, and that's going to give me, now I can convert to logarithmic, to exponential form. So 10 to the power of 12.5 equals IC over I naught. And therefore, the intensity of the concert is 10 to the 12.5 times I naught, right? And if we look here, okay, this is actually looking pretty good because remember, we're going to divide this by this. So the fact that we don't know this actually doesn't end up mattering, right? It's going to cancel out, which makes sense because we were just looking for how many times greater this was than this. So that constant doesn't actually change how many times greater it's going to be, right? All it does is change the, how many, it's not going to change, what am I saying? That constant isn't going to change how many times greater than it is. It's going to change like the actual measurement of it, sure, but it's just going to change, it's not going to change how many times greater the concert is than the radio, okay? So here we go. Let's now do the final step. How many times greater, right? We're finding the factor by which the concert is more intense than the radio. So to do that, we'll take the intensity of the concert and divide it by the intensity of the radio. And we get that the intensity of the concert is, well, we figured out that was 10 to the power of 12.5 times the reference intensity, over the radio was 10 to the power of 6 times the reference intensity. And sure enough, Reference intensity over reference intensity, those can just cancel out. And concert over the radio is just 10 to the power of 12.5 over 10 to the power of 6, which you could put in your calculator, but we might as well just use our exponent laws to simplify that, right? That just equals then, we can subtract those opponents, so 12.5 minus 6 is 6.5. 10 to the power of 6.5, now it's calculator time, but that gives us 3,162,278, right? So the concert is actually 3 million times more intense than the radio, right? So see how logarithmic scales sometimes can kind of hide how much more dramatically large a value is, right? But that's because there's this huge range. Just going from a radio to a concert, we're increasing the sound intensity by a factor of 3 million. So you can see why we come up with these logarithmic scales to give us a more convenient way of representing these things that have a huge range, right? So that means the concert is that many times more intense. It's releasing 3 million times more sound energy per second than the radio, okay? So that 125 decibels, though it kind of sounds like it's only twice as much sound energy, only twice as loud as this one, it's actually 3 million times more intense, 3 million times more sound energy being released, okay? And so again, the same goes for any logarithmic scale, your pH, your Richter, right? A earthquake that is a 4 magnitude might seem like it's only twice as bad as a one with a magnitude of 2, right? 4 seems like it's twice as big as 2, but because that's a logarithmic scale, it's actually 100 times as much energy, right? Because a difference of 2 really means a difference of 10 to the power of 2 by a factor of 10 to the power of 2. It's a logarithmic scale. Alrighty, so that wraps up the examples and notes for this lesson. All that's left to do is practice and ask me questions wherever you're stuck. I recommend try this one out right now. This is, while it's fresh in your brain, working with some, contextual logarithmic problems. But yeah, see if you can solve for this. This is an astrophysics one. I like this one, close to my heart. I love astrophysics. Okay, so go ahead, try that one out. And then that actually wraps up, folks. Believe it or not, that is the end of Unit 3. So your Topic 2 quiz for logarithms, once you've done your practice, you can do that, as well as you can now book a time to write the Unit 3 exam. As always, don't be shy, reach out for help, book a meeting, or just send me an email, whatever you prefer, or whatever's easier. And yeah, there we go. Unit 3, check. 3 down, 2 to go.